we extend our derivative concepts to the multivariate function by introducing the concept of gradient. The next one, I want to extend the function concept to a vector valued function. What means a vector valued function? Means the function return a vector instead of a scalar. Now look at this function. Let me give you an example. The function f equals 2 cosine t. Let me check. And the second one, we have the 2 sine t. The third one, 3t. Let me change the 2 to 4, maybe better. What I get is a curve in the space like this. We call it a helix. And that trajectory of the helix is represented as a vector valued function with 3 components. The first f1t is 4 cosine t. The f2t is 4 sine t. f3 is 3t. So the cosine, the sine represent a circle. You are doing rotation. And the vertical 3t means you are winding up. That's called a helix. So what kind of map is that? It maps to the single variable r, which is the time t, to a position in 3D. That's a real number to 3D mapping. You know, the previous example I gave you about the temperature and the position is a 3D to 1D mapping, right? This is like reversed. Okay, that's another type of function. You can also take a derivative. That's much easier. You can take a derivative one by one. If you take a double derivative, you take a double derivative one by one. So in the example above, if I want to take this derivative, then take the derivative, the 4 cosine is negative 4 sine t. Take the derivative 4 sine it is 4 cosine t, and take that is 3. What does that mean in geometry? Well, let's say this is your t, represented the vector of this tangent direction again. Even it's a vector, you know, in 3D, any vector is in 3D. You have 3 components. Let's put the t equal, let's say pi over 2. How about that? Then it's going to be negative 4 and 0, 3. That's the direction of the vector, of the tangent line. Take the double derivative. You can do it again. It's going to be negative 4 cosine t, negative 4 sine t, and 0. And this represented the centripetal force. Double derivative times the mass in Newton's law, you know, is the force. And in physical science, you can think this is the centripetal force to hold it to rotate. Or you can, in geometry, think about this is related with the curvature. So all have meaning. But this part is easy. You just do it. We call it component-wise, one by one. Now, are you ready? We're going to move over an even harder context. In that example, you are going to have a 3 independent variable function and the 3 dependent variable. That is from the 3D to the 3D map. That's not quite new. Our linear transformation discussed in last module is just like that. You can have 3 variables mapped to another 3 variables. But that's linear, you can always write it into a matrix. If it's linear, you take a derivative, it's always a constant. That's why it's a plane or superplane. But we can have a function. What kind of function you have in real world? Now, think about you have this automobile or autonomous vehicle. And the vehicle moves in the 3D space. The position you give need x, y, z to give the location of the vehicle. But the vehicle have a velocity. At that particular position, the velocity is another vector. The velocity could go like this, and you have 3 components. The velocity at the x direction, let me call this as east or north. And this Vx stands for the northward velocity, speed. And you have a velocity to the east direction. And you have a velocity like an airplane to upward or downward. And we have 3 velocity. Then we got 3 functions. Each of them are functions of x, y, z. I'm going to give you an example soon. Now let's put it that way. Like x, y, x squared z, x, z square. That's a 3 to 3 function. And you can try to understand this by the example I give. I give you x, y, z, only you know the position. But what you really interested is at that position, what is the velocity of the vehicle, of the UAV, AUV. And the velocity have direction, not only the magnitude. So to study a simple question like this, navigation, you definitely need this language. So how we are going to define derivative? The derivative, we call it a Jacobian matrix. You remember, when you have 3 variables and the single return value function, you got a gradient, right? So let's check one by one. You look at the first column, what you get is the first function. You take a derivative to x, take a derivative to y, take a derivative to z. That's the gradient of the first function. The second line, you pick the f2, and you take a 3 partial derivative. Then second row is the gradient of the second function. So the third is the gradient to the third function. A Jacobian matrix, in this case, is a 3 by 3 matrix. It's made by 3 gradient vector functions. When you learn the Cal 3, in the end, you talk about how do you change coordinate system. When you change coordinate to do triple integral, you're going to learn this Jacobian determinant. Let me see. Okay, Jacobian determinant. You just need to look at the determinant of the Jacobian matrix. So what is this determinant give you? Instead of 9 functions, the determinant is going to give you 1 function, a scalar function, after you finish the result. So here, no mistake. You get the 9 functions as a matrix. And the determinant, you got only 1 function. You're going to multiply them. We're going to look at example.